I have a microwave over here and I'm gonna place a cup of water inside it. Let's observe what happens and let's open it. As you can see, there's visible water vapor on the inner walls of this glass. So, how did this microwave heat my cup of water without any visible fire, coil, or heat? As we know, energy is equal to power multiplied with time taken. My microwave is rated at 800 watts and across 60 seconds, energy is going to be equal to 800 times 60 seconds. And final energy is going to be equal to 48,000 joules. As we know, heat energy is equal to mass times specific heat capacity multiplied with the temperature. For 100 grams of water, change in temperature would be 114 degrees Celsius. So, where does this heat energy come from? And how does electric energy get converted into heat energy? This is the general structure of a microwave. It has the magnetron at its core. Our magnetron consists of a central cathode with anode surrounding it and two permanent magnets placed above and below it. When electricity passes through our cathode, it releases electrons. Now, these electrons would just dash into the anode. However, the two permanent magnets placed above and below our system create a magnetic field that is perpendicular to our electric field. Our electron would experience force both directions. By left-hand rule, our electron would follow a circular path, as you can see over here, and it experiences a force called the Lohertz force. Over here, F is force, Q is electric charge, E is external electric field, V is velocity, and B is the magnetic field. The anode block contains copper keyhole shapes called cavities. As spokes or group of electrons sweep past these openings, they use the negative charge to repel away copper's internal electrons. This creates capacitance which stores electrical energy at the gap. But the electrons don't stay there. They repel each other and move through the circular back of the cavity. This movement creates inductance. However, they repel each other again, and because of the 90-degree phase swap, the energy sloshes back and forth between the electrical field in the gap and the magnetic field in the circle at a resonant frequency of 2.5 gigahertz. Now, you may wonder, why is it exactly at 2.5 gigahertz? The size of these copper cavities isn't random. They are precisely machined so that the distance around the circle is a fraction of the wavelength, which is approximately 12.2 centimeters. This creates resonance where the electrical and the magnetic fields slosh exactly at 2.5 gigahertz. That is approximately 2.45 billion times per second. The electric field energy density is equal to half of permittivity of free space, a constant, multiplied by the square of magnitude of the electric field. The magnetic field energy density is equal to 1 over permeability of free space multiplied by 2 of the magnitude of the magnetic field vector squared. Now, both of these fields exist together and hence the total density is equal to sum of these two constants. However, since the total sum is constant, we can conclude that these two terms are inversely proportional. To get the energy out of the cavities, we use a small copper tubulin loop or a hook inside one of the magnetic cavities. As the magnetic field grows and shrinks, it zaps the loop, creating a high frequency alternating current. Now, you may wonder why we only use one coupling loop. Because all the cavities are phase locked. They vibrate as a single unit, so draining energy from one cavity drains it from all of them. Using a single loop prevents destructive interference and ensures all the waves stay synchronized as they travel to the antenna. This alternating current travels up to a quarter wave of the antenna because the antenna is exactly one quarter of the wavelength, which, if you recall, is around 12.2 centimeters. It creates a high voltage anode with maximum pressure at the tip, launching energy into the air in the form of electromagnetic waves. These waves enter a waveguide, a hollow metal pipe that acts like a mirror-lined hallway. The waves cannot penetrate the walls, so they reflect in a sort of zigzag pattern towards the oven. A mica sheet acts like a window, letting the waves through it while keeping the food splatter and dust out of the electronics. Once inside the oven, these waves hit our water molecules. Our water molecules are polar, with the oxygen atom being the slightly negative end and the hydrogen atoms being the slightly positive end. The swap in electrical fields of the microwave reaches into these molecules and grabs these dipoles through a process called dipole rotation. The water molecules try to flip 2.45 billion times a second. However, they can't quite keep up, creating a phase lag that results in molecular friction. This friction returns the electromagnetic energy into heat and cooks